Second type of point defect. Second type of point defect is non-stoichiometric defect. It means after the defect, the ratio of atoms with respect to each other changes. Non-stoichiometric defect changes in the molecular formula. Non-stoichiometric defects is of three types: metal excess due to anion, metal excess due to cation, and metal deficiency defect due to cation. Now we discuss these three defects one by one. First type of non-stoichiometric defect. Non-stoichiometric defect is of three types earlier discussed: metal excess defect due to anion, metal excess defect due to cation, and metal deficiency defect due to cation. Now the first one, metal excess defect due to anion. In this defect, some of the anions are missed from their lattice site. Anionic species are missed from their lattice site and causes an anionic vacancy. That anionic vacancy traps an electron. Like when sodium chloride, which is white in color, white salt, is heated in presence of sodium vapors, then its color changes from white to yellow. And that yellow color exists because the sodium vapor releases the electron. These electrons are trapped in the anionic vacancy. These free electrons absorb the white light and shows colors. The site at which electrons are trapped, that site is called F center. So repeating, F center is the site at which free electrons are trapped in the anionic vacancies. In the similar cases, potassium chloride is again white salt. When it is heated in potassium vapors, its color changes to violet. Similarly, LiCl, lithium chloride, is also a white salt. When it is heated in lithium vapors, it is converted to pink. These three are the most common examples of metal excess defect due to anion. Anionic vacancies are created. These anionic vacancies are occupied by the free electrons. That site at which free electrons are occupied is called F center, and due to the presence of free electrons, it causes colors in the different compounds. Second type of non-stoichiometric defects. Non-stoichiometric defect in which molecular formula changes. Anion to cation ratio changes. Non-stoichiometric defect. Metal excess defect due to cation. In this case, some of the extra cations are present in the interstitial sites along with the free electrons to maintain the neutral crystal. Remind, these defects are also exist in ionic compounds. When extra cation and free electrons are available at the interstitial sites, then the defect is called metal excess defect due to cation because the number of cations increases. When number of cations increases, then molecular formula changes, stoichiometry changes. So this is non-stoichiometric defect. Most common example for non-stoichiometric defect, metal excess defect due to cation, is the zinc oxide. When the white zinc oxide crystals are heated, then it is dissociated into zinc cation, half O2 and 2 electrons. Due to the presence of these 2 electrons, the white compound zinc oxide is converted into yellow colored zinc oxide compound. These free electrons absorb the white light and shows the yellow color. Due to the presence of free electrons, the conductivity of zinc oxide also increases. We know that the ionic compounds are less or bad conductor of electricity, but after heating they becomes good conductor of electricity because zinc oxide release 2 electrons after heating. These 2 electrons increases the conductivity of zinc oxide. Type number 3. Type number 3 of non-stoichiometric defect is metal deficiency defect due to cation. Means deficiency of cation will be there in the crystal. So I am assuming that this is a crystal having ionic spaces positive and negative. If we remove 2 positive charge, 1 positive and 2 positive, then there are 2 vacancies created. To maintain the neutrality of the crystal, we have to add 2 positive charge. but with the help of only one cation having two positive charge. Two positive charge was removed and two positive charge is added. So the total charge is same, but there is one vacancy created for the cation. So total charge doesn't change, but number of cations decreases. So this is called deficiency of cation. In this defect, higher valency cation displaces the lower valency cation and causes the defect. For example, iron oxide, FeO. It consists Fe plus 2 and oxide ions 2 negative. When a mixture of plus 2 and plus 3 atoms exist in the crystal, then it becomes defective and forms Fe3O4. Some of the Fe2 cations, Fe2 positive cations are displaced by Fe3 cations and it becomes Fe3O4. As the process continues, as the defect exists continuously, it is further changes to non-stoichiometric formula Fe 0.95O1.00. One more example for metal deficiency defect due to cation is the nickel oxide NiO. Ni is at plus 2 state and oxygen at minus 2 state. When the plus 2 divalent cations are displaced by trivalent cation, then it forms Ni 0.98O1.00 crystalline structure. So this is the type number 3 defect of non-stoichiometric defect. These two most common examples of the non-stoichiometric molecular formula. Type number 3 of point defect. We earlier studied the two types of point defects, stoichiometric point defects and non-stoichiometric point defect. Now the type number 3 is impurity defect. Impurity means the foreigner atoms which are not responsible for the formation of crystals. Like I am assuming the ionic crystal having positive and negative charges. When we remove two positive charge, the first cation and the second cation. Now we can replace the cation with cation. Now we have to add any cationic species having higher valency. So one of the cationic vacancy is created. Number of cation decreases. This is just like the non-stoichiometric defect, metal deficiency defect due to cation, but in that case iron atom Fe2 plus is displaced by Fe3 plus, but in this case Na plus is displaced by strontium divalent cation. Now in this case strontium is not responsible for the formation of NaCl, sodium chloride crystal, but it is added as an impurity. So the defect caused by Sr strontium divalent is called impurity defect. Remind, any property having extra electrons or extra holes, maybe extra cation, maybe extra electrons, that increases the conductivity of the crystals. If there is a hole, if there is an extra electron in the crystal after the defect, then the conductivity of the crystals is always increases.